Imagine plummeting through the darkness of space, pulled inexorably toward a point of infinite density where the laws of physics tear apart everything you thought you knew. The closer you get, the more surreal and terrifying the experience becomes. Time stretching, light bending, horizons shrinking into nothingness. You might scream, but no sound escapes the vacuum. And yet, your senses are overwhelmed by a swirling vortex of cosmic mystery. With every millisecond, you could be heading toward a fate far beyond comprehension, where space and time fold into themselves. Stick around, because understanding what happens if you fall into a black hole isn't just mind-blowing. It's a journey into the very fabric of the universe itself. The nature of black holes. Black holes are among the universe's most mysterious and extreme objects, formed from the remnants of massive stars that have exhausted their nuclear fuel and collapsed under their own gravity. Their defining characteristic is the event horizon, a boundary beyond which nothing, not even light, can escape. This makes them invisible in their traditional sense. We only detect their presence through their effects on surrounding matter. The core of a black hole, called a singularity, is where densities become infinite and known laws of physics break down, leaving scientists pondering the true nature of reality itself. The intense gravitational pull of a black hole warps spacetime profoundly. If you could somehow stand at the edge, you'd see that space itself bends inward toward the singularity. As something approaches the event horizon, time dilates, meaning it slows dramatically relative to an outside observer. For an object falling in, time appears normal until approaching the singularity, but to someone watching from afar, its descent appears to freeze at the boundary. Frozen in place, almost like they're suspended in a cosmic limbo. The curvature of spacetime near the event horizon is so severe that it creates tidal forces capable of stretching objects into long, thin strands in a process often called spaghettification. In reality, black holes aren't just cosmic vacuum cleaners devouring everything in sight. They are complex entities predicted by Einstein's general theory of relativity. Their formation occurs when a star exceeds a certain mass limit, causing its core to collapse in a catastrophic implosion. Some black holes are stellar mass, formed from individual stars, while others, supermassive black holes, reside at galaxy centers, weighing millions or billions of times the mass of our Sun. There's even speculation about the existence of primordial black holes, formed in the universe's earliest moments, which could be much smaller or have different properties. The physics around these objects reveals insights about gravity, quantum mechanics, and the very structure of the cosmos, making them endlessly fascinating and puzzling. Black holes defy our everyday intuitions. Their existence suggests a universe where the fabric of space and time is malleable and where gravitational fields can reach unimaginable intensities. Some theories propose that the singularity might be a gateway to other dimensions or realms, but such ideas lie well beyond current experimental validation. What remains undeniable is that black holes embody the ultimate extremes of physics, challenging the limits of human understanding and inviting us to rethink what is possible in the universe's vast, dark corners. Event horizon, the point of no return. As you approach a black hole, the concept of the event horizon begins to feel less like a distant boundary and more like an inevitable crossing with profound implications. This boundary isn't just an arbitrary edge. It's the point beyond which nothing, not even light, can escape the black hole's immense gravitational pull. Once past this threshold, all paths lead inward, and the universe outside becomes fundamentally unreachable. The gravity here is so intense that spacetime itself warps dramatically, tugging at everything with relentless force. To your senses, this might manifest as a phenomenon called gravitational redshift, where light emitted from just outside the horizon shifts toward the red end of the spectrum, making objects appear dimmer and more distorted. Journeying closer to this boundary, you would notice that the universe behind you appears increasingly compressed and blue-shifted, its light stretched from your perspective to higher energies. The tension of impending doom is countered by a strange awe. Approaching such a boundary is like peering into an abyss that not only consumes matter, but also the very fabric of time and space. A key aspect of the event horizon is that it is a one-way barrier. The laws of physics, as we currently understand them, suggest that once you cross it, there is no returning, no bouncing back, no chance to communicate with the outside universe again. Instead, you are irrevocably drawn inward, heading toward the singularity, an infinitely dense point where traditional physics breaks down, and our understanding becomes a puzzle. For a hypothetical traveler, the crossing into the event horizon would likely be silent and instantaneous, because the concept of falling in involves stretching, squeezing, and ultimately spaghettification due to tidal forces. Near the horizon, these tidal effects depend on the size of the black hole. For supermassive black holes, the gravitational gradient at the horizon can be relatively gentle, allowing an astronaut to pass through without immediate destruction. Yet, for smaller black holes, the difference in gravitational pull from feet to head would occur rapidly, shredding any matter in an agonizing process. Once crossed, all signals sent outward would be impossible to escape the black hole's grasp, trapped by the overwhelming curvature of spacetime. The event horizon represents the ultimate boundary between the known and the unknowable, standing as a cosmic reminder of the limits of human understanding, an invisible, unyielding wall that marks the edge of reality as we comprehend it. Spaghettification, tidal forces at play. As you plunge deeper into a black hole, the difference in gravitational pull between your head and your feet, known as the tidal force, grows exponentially stronger. The gravity near the event horizon, the boundary where nothing can escape, reshapes your sense of physical reality in ways that defy common experience. If you imagine standing upright, the black hole's intense gravity is pulling more strongly on your feet than on your head. Think of it as a cosmic tug-of-war that's relentless and unforgiving. The core principle is that gravity does not diminish evenly with distance in such extreme environments. Instead, it creates a gradient so steep that it becomes impossible to escape. This gradient of gravitational force stretches and compresses your body along the axis of the black hole, a process called spaghettification. Picture this: your feet, closer to the singularity, are being pulled with immense force, while your head experiences slightly less gravity. As a consequence, your body begins to elongate into a thin, noodle-like strand. Hence the vivid, if unsettling, term spaghettification. The sensation is akin to being gently tugged, stretched, and slowly turned into a piece of cosmic pasta. During this process, your body would feel like it's being continuously elongated, muscles, bones, and tissues all succumbing to the relentless pull, torn apart on a molecular level. The process intensifies rapidly once you cross the event horizon, particularly for smaller black holes where the time dilation near a black hole. As you sink closer toward the event horizon of a black hole, one of the strangest and most mind-bending phenomena you're likely to notice is how time itself begins to stretch, distort, and behave unpredictably. Near a black hole, gravity becomes so intense that it warps spacetime to an incredible degree. For an outside observer watching you from a safe distance, your passage through time appears to slow dramatically as you approach the edge. From their perspective, you might seem frozen in place as your movements become sluggish, your clock seemingly ticking at a crawl. Yet, from your own point of view, time continues normally. Your heartbeat and thoughts flow in a steady rhythm, even as the universe outside accelerates into chaos and rapid change. This divergence in temporal experience hinges on the strength of gravity exerted by the black hole. According to Einstein's theory of general relativity, gravity is not just a force but a curvature of spacetime. Closer to the black hole, this curvature intensifies to the point where light itself is bent and stretched. You, traveling inward, would experience a kind of surreal, almost hypnotic slowdown. Seconds might feel like minutes or even hours from a distant observer's standpoint. If you could somehow communicate with someone far away, they would hear your voice slow to a crawl, your signals arriving increasingly delayed. Meanwhile, your own perception remains unaffected. You feel normal, but the universe around you appears distorted and frozen in time. The effects are even more extreme when you consider the physics at play near the event horizon, the boundary beyond which nothing can escape. To someone falling in, assuming they could survive the forces, time would seem to pass normally at first. But as they get closer to that invisible boundary, the fabric of spacetime itself becomes so warped that the concept of now becomes meaningless. In some ways, the person might feel like they are just crossing into another realm where conventional laws of time break down completely. The universe behind them appears to speed up, while they are stuck in a seemingly unmoving moment, with the background universe accelerating beyond comprehension. Interestingly, This inhomogeneous experience of time creates a paradoxical situation. From the perspective of the black hole's gravity well, your clock slows down to a crawl, almost as if you become increasingly frozen in a single moment. Yet, from your own perspective, nothing strange happens. Your thoughts and sensations continue uninterrupted. If you could somehow watch yourself from afar, you'd see you gradually fade into what seems like a ghostly stillness, while the universe at large races forward. This mismatch is a core part of why black holes are such fertile ground for theories about the nature of space-time, time travel, and the universe itself. An eerie reminder of how fragile and strange our experience of reality really is when faced with the universe's most intense gravitational forces. The journey inside, crossing the event horizon. As you approach the event horizon, the boundary where nothing, not even light, can escape the black hole, you begin to experience the universe from a perspective nearly impossible to grasp. For an outside observer, you would appear to slow down dramatically as you near this point, your motion stretching out and fading into a ghostly shimmer due to gravitational time dilation. But from your point of view, time continues to flow normally, though your surroundings will be changing in profound ways. The fabric of space-time itself becomes increasingly warped, stretching and twisting as you draw closer. Crossing the event horizon is not necessarily an instant calamity or dramatic splintering as often depicted in science fiction. Instead, it's a gradual process. You might see distant stars and galaxies twist into strange shapes, warped by intense gravity. If you somehow had the means to survive the journey, you'd notice that space and time are no longer behaving as they do elsewhere. What once felt like a stable universe begins to distort into a surreal, unrecognizable landscape. In principle, crossing the event horizon does not guarantee immediate destruction, unless you're a small, spaghettified object, but the true difficulty lies in what happens next. Once inside, the concept of a future becomes meaningless. The black hole's singularity, where gravitational forces are thought to be infinitely intense, lies inevitable ahead, pulling everything inward with relentless strength. Your body would start to experience spaghettification, a process where the difference in gravitational pull between your feet and your head stretches you into a thin, elongated shape. The experience is bizarre and terrifying, as your body succumbs to the gravitational gradient. Light from objects outside the black hole would be cut off, leaving an image of darkness surrounding you, punctuated only by the faint, distorted glow of what once was the universe outside. No matter how advanced your technology or how prepared you might think you are, crossing into the black hole's interior is a one-way journey punctuated by incomprehensible physics. Inside, classical notions of space and time break down completely, giving way to theories that remain speculative and elusive. Some models suggest that you would be inevitably drawn toward the singularity, where all known physics stops working. Others speculate that black holes could connect to other parts of the universe, wormholes or portals, though no evidence confirms this. Still, once inside that boundary, escape is impossible. You are at the mercy of a gravity so intense, it redefines reality itself, transforming the act of crossing from a moment of curiosity into an inexorable plunge into the unknown. The singularity, the heart of darkness. Deep within the swirling maelstrom of a black hole, where gravity bends reality to its will, lies the mysterious heart known as the singularity. It's not just a point in space. It's an almost unimaginable realm where the fabric of space-time itself contorts beyond recognition. As you get closer, tidal forces stretch and compress everything, your body, your instruments, the very particles making up your existence, into an almost incomprehensible state. The laws of physics, as you understand them, abruptly break down here. It is the final frontier of scientific inquiry, but also the ultimate trap, where current models offer no firm understanding. The singularity is often described as a point of infinite density, a place where gravity becomes infinitely strong and space-time curves into a bottomless abyss. The intense gravity of the singularity pulls relentlessly, and once crossed, escape becomes impossible. Closer investigation of black holes shows that just outside the event horizon, the boundary you can think of as the point of no return, lies the region where these distortions escalate dramatically. Falling inward, you'd experience what's called spaghettification, where gravitational differentials stretch you into long, thin strands. But past that, the real mystery begins. If somehow you could survive the crushing forces, you'd find yourself at the core, the singularity itself. Here, the normal rules that govern matter, radiation, and even spacetime cease to apply. Instead, you confront a core of infinite density, where our understanding of physics offers no meaningful description. In this realm, the equations that describe gravity, Einstein's field equations, predict singularities that are essentially mathematical artifacts, the breakdown points of general relativity. Physicists suspect that a theory of quantum gravity might eventually explain what truly happens, perhaps smoothing out the infinities into something comprehensible. Until then, the singularity remains an arrow pointing to the limits of human knowledge, a dark heart where space and time collapse into a single, contradictory point. It's a place where everything you've known dissolves, leaving only speculation, mathematical fiction, and a profound sense of awe at the universe's deepest mysteries. Studying the singularity isn't just an academic endeavor. It's a quest to glimpse the boundary where reality as we grasp it ceases to exist. What you would experience personally. If you somehow found yourself hurtling toward the abyss of a black hole, the very fabric of your reality would begin to warp almost instantly. As you approach the event horizon, the point beyond which nothing escapes, the intense gravity would exert differential forces on your body, a phenomenon known as spaghettification. Your feet, if you were falling feet first, would feel a relentless tug longer than your head, stretching your body into an elongated strand of flesh and bone. It's not just a metaphor. This stretching effect, caused by gravity's gradient, would produce a sensation of being pulled apart inch by inch. The closer you get, the more extreme these forces become, until survival becomes impossible. Yet, paradoxically, for a fleeting moment, there's a strange calm, because this process is so rapid that your conscious mind might experience a surreal distortion of time and space. Despite the violent forces at play, your personal experience of falling would begin with a strange kind of awe. Time outside the black hole would appear to slow, and every second stretching into what feels like minutes as you cross the event horizon. From your perspective, you might see the universe ahead seeming to flicker and fade, distant stars flickering like candles in a breeze. Light from outside the black hole would be heavily gravitationally lensed, bending around the curvature of spacetime, creating warped images of distant galaxies. These visual distortions could be mesmerizing, like glimpsing a hall of mirrors with infinite reflections, until reality noticeably shifts. Your own body might seem frozen or distorted, but your mind still painfully aware of this gradual unraveling. Once past the event horizon, the experience would become more incomprehensible. The universe outside would be forever out of reach, cut off by the point of no return. The sheer density of the black hole's core, where matter is crushed into an infinitely small point, a singularity, means that the laws of physics as you know them break down. The gravitational forces would be overwhelming, warping spacetime so significantly that concepts like up and down lose all meaning. Your perception of time may become utterly distorted. What feels like hours could be seconds or vice versa, a consequence of near-infinite gravitational time dilation. You would be hurtling inevitably toward this singularity, an environment where quantum mechanics and general relativity clash, hosting a potential gateway to the unknown as you drift toward the core. In that final stretch, you would confront the limits of human sensation and comprehension. The universe would vanish behind a horizon of complete blackness, swallowed in the depths of a gravitational well so deep that even light cannot escape. Your sense of self would probably dissolve in the face of such extreme forces, your consciousness teetering on the edge of understanding before succumbing to the inevitable. The experience is impossible to fully describe because it defies the very laws that make experience possible. It could be seen as both terrifying and profoundly awe-inspiring, an ultimate encounter with the universe's most enigmatic and powerful phenomena. The truth is, if you fell in, what you experience personally would be a fleeting yet eternal act of surrender to the universe's most extreme, mysterious boundary. The fate of your physical body. If you somehow managed to fall into a black hole, your physical body would undergo a series of unfathomable transformations, each one more extreme than the last. As you approach the event horizon, the point beyond which nothing can escape your fate is sealed. Time itself seems to stretch and distort. From your perspective, if you could somehow witness it, You might see external stars and galaxies racing past in a blur, while your own body begins to feel an odd, tingling numbness at first. But that's only the beginning. The intense gravitational pull starts to dominate every cell, every atom. Once you cross the event horizon, the notion of your body remaining intact becomes increasingly implausible. The gravitational forces inside a black hole are so colossal that they create a state called spaghettification. This cosmic process stretches your body lengthwise into a thin strand, akin to spaghetti, hence the nickname, while simultaneously compressing it widthwise. The gradient of gravity, called a tidal force, becomes so steep that atoms are ripped apart, molecules disassembled, and the cohesive bonds of your tissues dissolved into an unrecognizable chaos. In the final moments before reaching the singularity, your physical form would be a distorted smear of matter, stretched beyond recognition. What happens at the core of a black hole at the singularity remains one of the greatest mysteries in physics. Classical physics suggests that all the matter that comprised your body would be crushed into an infinitely small point, an infinitely dense point where space and time lose their meaning. But this concept doesn't account for quantum effects, which might prevent such a crushing fate or rearrange the ultimate fate of matter in ways we cannot yet comprehend. Your body, which was once familiar and solid, would effectively cease to exist as a biological entity. Instead, atoms and subatomic particles would be compressed into a state that defies normal physical laws, likely contributing to the overall mass of the black hole itself. In essence, falling into a black hole would obliterate the physical identity you cling to. The sensation of falling, if it could be felt, would give way to an overwhelming pressure, endless stretching, and finally total disintegration. The process is rapid once past the event horizon, but in reality, from an external observer's point of view, your death would appear to take eternity. For you, inside the black hole, reality turns into an incomprehensible swirl of distort. Reflections on theoretical observers. When you venture toward the event horizon of a black hole, assuming such a journey is even possible, the concept of a theoretical observer becomes a puzzle wrapped in paradoxes. To understand this, think of a distant observer watching you fall in. From their viewpoint, time appears to slow down as you approach the event horizon, your movements stretching into an almost imperceptible crawl due to gravitational time dilation. They see your signals, your light, becoming increasingly redshifted, fainting into the cosmos' distant glow. Yet, from your perspective, things seem quite different. You'd swiftly cross the threshold, with no sudden change at the horizon itself, feeling only gravity tugging relentlessly downward. A theoretical observer positioned far away in asymptotically flat space would argue that your fall is never truly complete because they would never see you fully cross the event horizon. The light from your crossing would take increasingly longer to arrive, stretching indefinitely due to the extreme warping of spacetime. But for you, trapped inside the black hole, the story looks different. You'd experience a finite amount of proper time before your inevitable, violent encounter with the singularity, where general relativity predicts densities so extreme that the fabric of spacetime itself seems to tear. For this observer, the horizon is just a feature, an apparent boundary with no special physical properties. Yet the singularity is a cardioid of destruction that awaits. This disconnect reveals a fundamental tension in black hole physics. The coexistence of two seemingly incompatible descriptions based on where the observer is. It challenges notions of reality itself. While the distant observer's frame insists on a universe where crossing the horizon is an asymptotic process, the infalling observer's experience is one of free fall, no fanfares, no warning, just an acceleration into the unknown. Such divergent perceptions propel ongoing debates about how to reconcile quantum mechanics with gravity. If you were to place yourself in the shoes of a hypothetical observer hovering at a safe distance, the very act of witnessing your demise through the black hole's veil would be a feat of patience and curiosity. But if you could somehow experience falling in, the event horizon would seem almost mundane, until the crushing pull of the singularity reminds you that no observer can escape its finality. The paradoxes deepen further when contemplating what information you carry, a core question in theoretical physics. From afar, you might appear as a flickering light, gradually dimming as your signals shift and stretch. But the question remains, what happens to the information about your state once you cross the horizon? Is it lost forever, Or does it somehow get encoded on the universe's boundary, as suggested by the holographic principle? Each perspective, each observer's frame of reference, exposes new layers of mystery. They beckon us to reconsider what reality truly is when weighed against intense gravity, leading to profound reflections on the nature of existence, observation, and the limits of scientific understanding. Black hole information paradox. The core of the black hole information paradox lies in a clash between two foundational pillars of physics: quantum mechanics and general relativity. As you approach a black hole, the immense gravity warps space-time itself, pulling everything inward with such force that nothing, not even light, can escape once past the event horizon. According to classical physics, the information about whatever falls into a black hole, be it a star, spaceship, or particle, becomes lost forever beyond this point. Yet, quantum theory insists that information must be preserved, that the fundamental laws are reversible and no data can truly vanish. This creates a paradox as soon as you consider what happens to information when matter hits the singularity, an infinitely dense point where known laws break down. In the realm of quantum mechanics, particles behave in a way that fundamentally encodes information about their initial state. When matter enters a black hole, it seems that this information is obliterated, contradicting what quantum theory suggests about unitarity, the principle that the total information in a closed system stays constant. Hawking radiation complicates matters further. As black holes emit this thermal radiation, they lose mass and eventually evaporate entirely. If the radiation contains no information about what originally fell in, purely random, featureless radiation, then the information about the initial state is essentially destroyed. This loss challenges a core consistency in physics. Can the universe erase its memory? Or is there some hidden mechanism that preserves information, but remains out of reach of current understanding? Some proposals involve the idea that information isn't lost but is instead imprinted onto the Hawking radiation in a subtle way, perhaps through quantum entanglement. The notion is that the radiation encodes correlations pointing back to the original matter, preserving some form of quantum coherence. However, the details remain elusive. Does the information escape the black hole gradually, like a slow leak, or is it stored at the event horizon in a scrambled state, as suggested by holographic principles? These questions stir the imagination because they suggest that black holes might be a testing ground for a theory of quantum gravity, an elusive framework unifying quantum mechanics and general relativity, something scientists have been chasing for decades. The paradox continues to spark debate because resolving it could revolutionize physics itself. It forces us to reconsider the nature of space, time, and reality. If information truly cannot be lost, then our current understanding of black hole physics is incomplete and maybe even fundamentally flawed. If it can be lost, then the implications threaten to overturn quantum theory's core. Researchers explore ideas like the firewall hypothesis or the scrambled information concept, each with dramatic implications. Falling into a black hole, you'd feel a strange mix of awe and dread knowing that whether your story survives depends on secrets still buried in the universe's deepest mysteries, lurking behind the event horizon's veil. Potential outcomes: escape, consumption, or transformation. If you somehow found yourself hurtling toward a black hole, the first thing to grasp is that escaping once you cross the event horizon becomes practically impossible according to our current understanding of physics. The immense gravity of a black hole warps spacetime to such a degree that nothing, not even light, can break free. If you were to fall into one, you'd be subjected to a process called spaghettification, stretching you out lengthwise as the gravitational pull intensifies exponentially. At the brink, the sensation might resemble an extreme tug, like being pulled apart by an invisible, relentless force. The very fabric of reality begins to fray, and your physical form would inevitably succumb to the black hole's destructive grip. But before you reach this point of no return, there's still a theoretical possibility, though staggeringly slim, that you might escape. This hinges on the existence of phenomena such as Hawking radiation, through which black holes can gradually evaporate over unimaginably long timescales. In a hypothetical universe where quantum effects or wormholes exist and are accessible, there might be a route to tunnel out or slip through a hidden portal. Current models, however, suggest that once inside the event horizon, escape is fundamentally forbidden by the laws of physics. Still, pondering whether a rogue spaceship or an advanced civilization could engineer a way out stokes the imagination, even if the cosmic odds seem stacked against it. As you approach what lies at the very core of a black hole, the singularity, your fate takes a turn towards the deeply enigmatic. The singularity is a point where gravity becomes infinite and space-time curvature blurs into a state that defies all existing physics principles. Some theories speculate that your matter might merge with the black hole's core, becoming part of an incomprehensible swirl of energy and space-time distortions. Others entertain the idea that the intense conditions could alter your very nature, effectively transforming you. In theories of quantum gravity, the singularity might resolve into a different state altogether, possibly a portal to another universe or a different point in space-time. Whether you would be consumed outright or somehow transformed into a fundamentally different entity hinges on physics we're still struggling to understand. The concept of transformation is where the scenario becomes uniquely disturbing yet tantalizing. If a black hole acts as a cosmic crucible, whether destroying or reconfiguring the matter it devours, you might be caught in a process that leads to near-instantaneous obliteration or to an extraordinary metamorphosis. Some speculative theories propose that black holes could seed the creation of new universes in a multiverse framework. In such a universe, falling into a black hole might not be the end but rather a transition, your essence adapting and emerging somewhere else, possibly in a universe with different physical laws or constants. The fascination with this scenario taps into the profound idea that black holes may be cosmic gateways rather than mere destructive zones, a concept that continues to stir scientific curiosity and philosophical debate. Implications for space travel and humanity. Falling into a black hole defies everyday understanding of physics, but considering the theoretical implications offers a profound glimpse into where humanity's curiosity could lead. If you somehow survive the trek, an impossible feat given the immense tidal forces, you would encounter a reality where space and time distort in ways that challenge the very foundations of physics. For space travel, this hypothetical scenario pushes us to consider the limits of technology and understanding. To reach a black hole's event horizon, spacecraft would need propulsion systems far beyond what is currently conceivable, capable of withstanding extreme radiation and gravitational gradients. Even if such technology were developed, the journey itself would raise questions about the nature of space-time manipulation and energy sources, possibly sparking new fields of physics research. On a wider scale, the notion of humans venturing close to or into black holes catalyzes discussions about the future of exploration and the survival of humanity. The immense gravitational pull stretching objects into long fibers in what's called spaghettification would highlight the destructive power of nature's most extreme features. Yet, contemplating this serves as a beacon for advancing astrophysical knowledge, deepening our understanding of gravity, quantum mechanics, and the fabric of spacetime. Such insights could eventually lead to breakthroughs in propulsion, energy harnessing, or even technologies that allow us to manipulate gravitational fields. Space agencies might see these black holes as natural laboratories to test the boundaries of physics, possibly unlocking new paradigms for interstellar travel or even harnessing black hole event horizons as sources of energy, much like Hawking radiation. For humanity, the implications extend beyond pure science. The experience of even imagining falling into a black hole is a potent reminder of our fragile planetary existence contrasted by the universe's grandeur. If humans ever learned how to approach these cosmic mysteries responsibly, without risking destruction, our perspective on life would shift dramatically. It would emphasize our smallness in the face of cosmic phenomena and inspire a new era of cooperation and innovation aimed at understanding the universe's most profound secrets. Such knowledge could eventually influence how we develop space habitats, survival strategies for interstellar travel, or methods for harnessing energy on a galactic scale, ultimately transforming humanity into a species capable of surviving and thriving amid the universe's harshest environments. Beyond the scientific and technological prize, the philosophical and cultural implications are staggering. Confronting the reality that black holes may connect to other universes or serve as portals to unknown realms presses us to rethink existence itself. It would challenge our notions of space and time, pushing us toward new philosophies about the nature of reality. Humanity's journey into understanding black holes could spark a renaissance of curiosity and humility, driving innovation while also fostering a deeper appreciation for our universe's mysteries. If these cosmic objects are gateways rather than dead ends, they could redefine the future of space exploration, pushing human consciousness into realms we previously only dared to dream of. Black holes and the universe's evolution. When you consider the role of black holes in the grand tapestry of the universe, their influence goes far beyond mere cosmic curiosities. These dense remnants of collapsed stars exert an intense gravitational pull that warps spacetime itself. Essentially, they serve as both endpoints of stellar evolution and catalysts in the cosmic cycle. As the universe expands and galaxies collide, black holes remain as anchoring points within their host galaxies, affecting star formation and galactic dynamics. In fact, supermassive black holes, sitting at the centers of galaxies, including our Milky Way, are thought to regulate the pace at which galaxies grow and evolve. A growing field of research suggests that black holes may even have played a role during the universe's infancy, influencing the formation of the first galaxies and cosmic structures. However, one of the most compelling aspects of black holes in the context of cosmic evolution involves their role as cosmic engines, transforming their surroundings through processes like accretion and jet emissions. As matter spirals inward, it heats up to incredible temperatures, radiating energy across the electromagnetic spectrum, sometimes outshining entire galaxies during active phases. These energetic outflows, called relativistic jets, extend vast distances into space, injecting energy and matter into the intergalactic medium. This feedback loop can suppress or trigger star formation in neighboring regions, subtly shaping the evolution of large-scale structures. In this way, black holes aren't just endpoints but active participants in the universe's ongoing development, influencing everything from small star clusters to the largest galactic superstructures. Furthermore, black holes might be integral to the universe's ultimate fate. Theories propose that if many galaxies harbor supermassive black holes, their merging during galactic collisions could lead to colossal black hole mergers, emitting gravitational waves, ripples in spacetime detectable across cosmic distances. These events could release immense energy, further affecting the surrounding cosmic environment. On a larger scale, the distribution and behavior of black holes could also influence the universe's overall expansion rate through their gravitational effects, especially if dark matter or dark energy interact with black holes in unforeseen ways. Some speculative ideas even suggest black holes might serve as portals or gateways, tying into larger considerations about the universe's structure and overarching evolution, though those remain highly theoretical. Throughout the universe's history, black holes function as both indicators and agents of change. Their presence signals past events, such as star deaths or galaxy mergers, and their activity can stir the cosmic soup, shaping the evolution of the universe over billions of years. As the universe continues to expand, black holes endure as unyielding anchors in the cosmic web, quietly influencing the ebb and flow of large-scale structures while embodying the profound mysteries still waiting to be unraveled. Speculating on future discoveries. As the universe continues to reveal its secrets, scientists are eager to push the boundaries of what might be possible in understanding black holes. One fascinating avenue of speculation revolves around future discoveries that could reshape our comprehension of these cosmic enigmas. Advances in telescopic technology, for instance, promise to sharpen our view of the event horizon, the boundary beyond which no information can escape. Instruments like the Event Horizon Telescope have already given us a glimpse of the supermassive black hole at the center of our galaxy, but future iterations could provide a resolution so detailed that we might finally observe the accretion disks and relativistic jets in unprecedented detail. Such observations could confirm or challenge current models of how matter interacts with extreme gravity. Moreover, the development of gravitational wave observatories has opened an entirely new window into black hole phenomena. Already, instruments like LIGO and Virgo are detecting ripples in spacetime caused by black hole mergers. With planned upgrades and next-generation detectors, the sensitivity will improve exponentially, potentially revealing a broader spectrum of black hole mergers, including those involving intermediate or even primordial black holes. These discoveries could provide clues about the origins of black holes and their role in the evolution of cosmic structure. Perhaps, in the future, we might directly observe the formation process of black holes in real time, catching the moment when collapsing matter crosses the event horizon. a feat that would radically enhance our understanding of gravitational collapse. Theoretical physics is also poised to leap forward thanks to breakthroughs in quantum gravity research. Currently, black hole information paradox and singularities remain giant mysteries. Future discoveries might include experimental evidence for phenomena like Hawking radiation, or even the detection of hypothetical particles predicted by theories beyond the standard model, like gravitons. If these particles can be observed indirectly, they could support or deny the existence of certain quantum effects at the event horizon, shattering long-held assumptions. Some scientists speculate that future discoveries might reveal that black holes are not entirely black after all. They could be gateways to other dimensions or contain fuzzballs, objects proposed by string theory, a revelation that would fundamentally change our understanding of space-time. Ultimately, imagining the future is to imagine a cosmos where black holes are not just mysterious cosmic vacuum cleaners but key to unlocking the nature of reality itself. Breakthroughs in technology and theory may one day allow us to see them not as infinite pits of doom, but as extraordinary laboratories of physics where gravitational and quantum realms intertwine. These discoveries could even lead to practical breakthroughs, such as new energy sources derived from understanding black hole mechanics or advanced propulsion systems inspired by their physics. With each new step, the black hole's shadow looms larger in the collective human quest for knowledge, an ever-present reminder of how much more remains hidden just beyond our current reach. Falling into a black hole feels like being stretched and compressed simultaneously at a scale that defies normal understanding. As you cross the event horizon, the boundary beyond which nothing can escape, the universe seems to turn inward. Light from the outside universe continues to stream in, but from your perspective it becomes increasingly distorted. Time itself starts to warp noticeably. Seconds stretch into minutes or hours from an external observer's perspective, but for you the passage feels rapid and surreal. You might feel a moment of intense weightlessness, followed by an overwhelming sensation of being pulled inward, as if the fabric of space-time is collapsing around you. Once beyond the event horizon, your journey accelerates towards the singularity, the core of the black hole where gravity becomes infinitely intense. Here, the laws of physics as we understand them break down. Spaghettification, a term scientists often use to describe the extreme tidal forces, becomes unavoidable. Your body would stretch lengthwise while compressing widthwise, like a piece of linguine being pulled apart. Despite that grim imagery, for a brief moment, your senses might be overwhelmed by a curiously vivid experience. The universe is dramatically compressed, with distant stars and cosmic background radiation rushing toward you in a final, chaotic burst. It's a scene that defies every instinct but remains rooted in real physics, even if incomprehensibly extreme. The true nature of what happens at the singularity remains one of the greatest mysteries in astrophysics. According to classic general relativity, the singularity marks a point of infinite density and zero volume, effectively a tear in the fabric of spacetime. But many scientists believe quantum effects, which are not yet fully understood, would intervene before reaching this point in reality. Some theories suggest that instead of a destructive end, falling into a black hole could connect to a different region of spacetime, like a wormhole or a portal to another universe. However, all current models are speculative. No direct evidence exists, and the physics at this stage remain intensely mysterious. If you somehow survive the journey, an impossibility according to current understanding, the experience would challenge everything you knew about reality, leaving questions about existence, space, and time shattered into fragments. As you drift into the darkness, the profound weight of the black hole's gravity pulls at every inch of your being, stretching time and space into a surreal tapestry. The intense spaghettification leaves you trembling on the edge of the unknown, caught between fear and awe. You've just glimpsed how these cosmic giants warp reality, transforming what we think we know about the universe. Remember, what we see and imagine about black holes is just the beginning. The mysteries they hold are still unfolding, waiting for us to explore further. If this sparked your curiosity, stay tuned. There's so much more to discover about the cosmos, from wormholes to dark energy, that could reshape our understanding of existence itself. So, whenever you're ready to take the plunge into the depths of space and time, know that the universe is vast, full of secrets, and eager for your curiosity. Until then, Keep gazing upward and wonder, because the universe never stops inspiring.